So today what we're going to actually look at is how to be able to integrate some functions that are composite functions. Okay? Now I've been telling you that integration is more challenging than differentiation because differentiation we had the product rule, the quotient rule, the chain rule. So even though it might get ugly, it might get complex, you could always use those rules and find the derivative. Okay? The same is not the case with antiderivatives. Alright, so there are some different methods. This is as close to as we get to a chain rule for integration. Okay, but don't call it that. What we're looking at here is integration by substitution. So just to first of all illustrate the whole idea, remember that the chain rule, the derivative of f of g of x would be f prime of g of x times g prime of x. So there's our chain rule. Derivative of the outside times the derivative of the inside. Okay? So at this point, if I were going to take the derivative of this function right here, I would use my power rule. Okay? So 2/3 times the 3/2 x cubed plus 1. You guys all know how to do this. And that would be to the 1/2 power because we subtract 1. And then I would multiply by a 3x squared. Okay? So that's 1, that's 1. This whole thing comes out to 3x squared radical x cubed plus 1. Okay? So that's all review. You know how to do that stuff. So think with me. What would the integral of 3x squared times the square root of x cubed plus 1 dx equal?
2/3 times x cubed plus 1 to the 3/2.
Close?
Plus c.
Plus c. There we go. Good. So 2/3 x cubed plus 1 to the 3/2 and then a plus c. Alright, great. Now, that seems kind of easy when you have already done the derivative. The integral gets you back to that same family of functions with just the plus c as the difference. Okay? But what we have here is we have a composite function that we're dealing with, and the composite function is this radical x cubed plus 1. And then you've got this extra piece here, the 3x squared, and of course the dx as usual. We're going to look at how to use those in order to actually rewrite this in terms of a different variable so that we can use the antiderivative rules that we've already learned. Okay? So here's the basic rule. The antiderivative of a composite function. If you have f of g of x times g prime of x dx, the integral will be the antiderivative of the outer function with g of x still inside, plus c. Okay? Now, we're going to simplify some notation here as we go along, but notice here, f is the outside function, g is the inside function, and g prime is the derivative of the inside function. Okay? So let's actually look at this by substituting a little bit. Okay? So here's what we have. This is what we're trying to prove. Okay? This is what we're trying to prove. The integral of f of g of x times g prime of x dx is capital F of g of x plus c. Okay? Now, there's a couple of things that we need to understand here. First of all, I'm going to let u equal g of x. And then you have this statement here. du is g prime of x dx. Well, where in the world does that come from? Let's take a look. If I were to take the derivative of u with respect to x, that of course would be g prime of x. Right? Well, this is du over dx. I'm going to multiply both sides here by a dx. That will cancel that out, and now I have du equal to g prime of x dx. Okay? That's a key part to this entire thing. So if I substitute the u's in, notice what I'm able to do, okay? G prime of x dx is the du, so I'm taking this right here and I'm going to replace it with this. Okay?
What is the u then?
The u is that inner function, okay? So whatever the inside function is, that g of x, I'm rewriting that as just a u to simplify it. Kind of like when we did chain rule, we made it f of u and it's f prime of u, u prime. Okay? Same idea. So now we replace that with just a u. And notice now we have a function that hopefully we have an antiderivative for. Okay? But notice the antiderivative is not in terms of x, it's in terms of whatever that function u was. Okay? So, let me go back to the example that we did up here and show you how this integral works. Okay? So, we had the integral of a 3x squared radical x cubed plus 1 dx. I want to show you this u substitution. Okay, so first of all, you have to look for the inner function. The inner function is going to be this x cubed plus 1. Alright, so that u is x cubed plus 1. Well, that means du dx is going to be 3x squared, and that means du equals 3x squared dx, because I multiply both sides by the dx. Okay? So now notice what we have. The du is 3x squared dx. That's right here. Okay? So now what I'm going to do is I'm going to substitute this in. I have the integral, I have the integral of the square root of u, that was that x cubed plus 1, alright? And then the rest of this is the du. Okay? So there's the du. I substituted that in. Now, tell me, what is the antiderivative of the square root of u?
2u to the...
You just put x cubed plus 1 in there.
2/3 u to the 3 over 2.
Well, hang on. We'll get to that. What?
2/3 u to the 3. 2/3 times u to the 3 halves.
Okay, 2/3 u to the 3 halves plus c. Okay? There's our antiderivative. The antiderivative of u to the 1 half, you add 1 to the exponent and divide by the new exponent. So divide by 3 halves, it's times 2/3. Okay? Now, just like with the chain rule, we don't want our answer in terms of u's, we want it in terms of x's. So wherever I see the u, I replace that with the x cubed plus 1. Alright, so it's going to be 2/3 times x cubed plus 1 to the 3 halves plus c. And that's exactly what we said it was up here. Okay? But that's the whole process. And you need to get into a routine. This one is going to be all about routine. We start with simple ones. We're going to increase complexity a little bit as we go along, but all of them have the same basic pattern that you're going to need to follow. Okay? So, let's just go through these real quick and just identify what the u is in each one. Okay? What is u in this first one?
X squared plus 1.
It's the x squared plus 1. Okay? How about in the second one?
Same thing.
Yeah, same thing. X squared plus 1. Alright, so there's our u. There's our u. What's u in the third one? X cubed plus 1. How about the fourth one? 5x plus 1. How about the next one?
Tan x plus 3.
Tan x plus 3.
Oh, yeah. Is it not?
What do you guys say?
Is it x times tan x plus 3?
It's secant squared of x times the tangent of x plus 3.
Oh, so it's just x plus 3.
No, tan x plus 3, not tangent of parentheses x plus 3.
Well, since it's square, is it is it x?
Let's think this one through. We'll work it out and we'll see if that works, okay? For both of those. So I won't highlight those ones. But how about the last one?
X cubed plus 1.
X cubed plus 1, okay? So, I know what u is for all of those. And you can think it through. Do this as kind of a routine. Write down your u first, okay? And then the next thing that we want to figure out is what is the du, okay? Now remember, it's du dx equals the derivative. So the derivative there would be 2x. So that's du over dx equals 2x. So what's du equal?
2x times dx.
2x dx, okay? So we multiply by dx. Du is 2x dx. Okay? That's not too bad. How about, well, the next one's exactly the same, okay? Du is 2x dx. How about the next one?
Du equals 3x squared dx.
3x squared dx, okay? Very quickly, we should get to the point where we don't have to write du over dx and then multiply both sides by dx. You'll notice what's happening every time. It's the derivative times the dx, okay? So, next one, du is
5 dx.
5 dx. And this last one,
3x squared dx.
there we go, 3x squared dx. Okay? You guys with me?
Yes.
Alright. Okay. So, we're going to hold off on these two until we get down there eventually, okay? So, the du's, whoops, highlighter. The du's, we're going to identify in the function, okay? So, the du is a 2x dx. So I'm going to rewrite this one as the integral of u to the fourth du. Okay? So, if I actually do the integral there, the integral of u to the fourth is
U to the 5th over 5.
u to the fifth over 5. We plug back in the x squared plus 1 for u, and it's x squared plus 1 to the 5th over 5 plus c. Okay. Ooh, that's no good. Okay. Let me separate this a little bit so we don't like that you can't move your text around real easily with this. Alright, but there's your answer, okay? Now, that's not so bad. Let's take a look at the second one. du is 2x dx. Where's our 2x dx? In the integral. We got the dx. We got the x. Where's the 2?
Derivative of the inside.
No, we need
Are we just going to multiply?
we need a 2 here. So is there any way we can stick a 2 here?
Sure. Let's do that and multiply the whole thing by 1/2.
Okay. So you're saying do this. Can we do that?
No, the entire thing.
Let's think about our antiderivative rules, okay? The integral of a constant times a function equals the constant times the integral of the function, right?
So we can do that.
So, in this case over here, what am I actually doing?
You were multiplying the function by 2, but because it's a constant, you can pull it out, and you have a 1/2 waiting for it, so it's going to cancel out.
Okay, because what are we really multiplying by? We're really multiplying by 1, right?
Mm-hmm.
As long as we multiply by 1, it's okay. Alright? Alright, so as long as we multiply by our identity, 1, we're not changing the problem, and in that way, we're then able to find the u, or I should say the du, that we need. Okay? So this problem then would be rewritten as a 1/2 times the integral of u to the 4th du. Okay? Again, the integral of u to the 4th is u to the 5th over 5, so it's 1/2 times u to the 5th over 5.
You just make it u to the 5 over 10.
So yeah, we're just going to make it u to the 5th over 10, and u is the x squared plus 1, so it's x squared plus 1 to the 5th over 10 plus the c. Okay? Alright, so we see a similar thing here in our next one. The du is 3x squared dx. I've got the dx. I've got the x squared. I'm missing the 3. So how are we allowed to do that?
Multiply by 1/3.
Multiply by 1/3. There we go. So multiplying by 3 over 3, it's just the numerator's in the inside and the denominator is outside. Okay? So this would be 1/3 integral of the square root of u du. Okay? The integral of square root of u, we said earlier, was u to the 3/2 times 2/3, but that is now multiplied by a 1/3. Okay? So now I have a 2, and it's over 9, and I'm going to plug in the u, which was x cubed plus 1, as to get my final answer, okay, in terms of x.
Why
Yes.
are we doing the thing where you multiply it by 1? Like by 2 and then 1/2 and then 3 and then 3.
Because what we saw back here is if you're taking the integral of f of u du, it'll be the antiderivative there, okay? Here, the du was already there. Du was 2x dx.
Okay.
Here, we were missing the 2, so we had to supply the missing piece and counter it so we weren't changing the whole problem.
Alright, I got it.
Okay? Here we have 5 dx. Okay? We have 5 dx, so there, 5 dx is our du. So this one we don't need to multiply by anything. It's just the integral of the square root of u du, which again is 2/3 u to the 3/2. So 2 radical 5x plus 1 over 3
Can you zoom in?
plus c.
Thank you.
Okay? Before we tackle the secant and tangent one,
Wait, I have a question. Why is it the square root of 5x plus 1? Isn't it to the 3
oh wait, yes, thank you.
Root of it squared.
Yeah, I could do the square root cubed, but that's not particularly helpful. Thank you. Okay. All right, try the last one here before we tackle the secant and tangent ones. All right, let's take a look at this one. What do you have?
Like we can use u here, but it's 3x, so we need to leave this, and it's like it's just use 2 over or 1 over 2. Then we do integral of u. But since we have this here, so if we substitute u in there, we should take this off.
Correct, yeah. Because we've got this, all of the du is already here. Okay? Because all of the u is right there already, we can simply do the integral of the radical u, or u to the 1/2, and then replace the rest of it with the du. And then it's actually the same as the other ones. It's u to the 3/2 times 2/3. And then we just plug it back in. So it'd be 2 u x cubed plus 1 to the 3/2 over 3 plus c. Okay? Plus c.
I keep forgetting
Alright.
about plus C.
So yeah, don't forget your plus c. So the previous two, the two that we skipped, this is where things can get challenging, because you think to yourself, okay, wait a sec. Do I make the secant squared my u? Do I make the tangent plus 3 my u? Is the u just tangent? How do I handle this? Okay? Well, you have to think, and you just have to try. So a number of you guys thought that the u might be the tangent x plus 3. Okay? So let's try that out. If u is tangent x plus 3, that would make du, the derivative of that, times dx. What's the derivative of tangent? Secant squared.
So that's gonna work.
Okay, so secant squared x, and what do you know?
It works out.
When we look at this, our du, there's secant squared x dx. So this is the integral of u du. Well, that's easy. The integral of u is u squared over 2. So, what's u squared over 2? It's tan x plus 3 squared over 2. And then you have plus c. And that's it.
So for the one underneath that, since it's 2 secant squared x, would you have to multiply it by 1/2 inside the integral, then 2 outside the integral?
You could think of it that way, or just think of it as, hey, I'm taking this 2 as a constant multiple and I'm pulling it outside. So however you think of it, it's simply going to be 2 times that integral.
So it's just gonna be u squared.
So it's going to end up being 2 times what we got on the previous problem.
So, like you said, just u squared.
Yeah.
2 times
It'd be 10
the u squared over 2. Oh yeah, sorry. It would just, the 2 and the over 2 would cancel each other out. Yeah. So 2 times tangent x plus 3 squared over 2 would just end up being tangent of x plus 3 squared plus c. Okay? So, that's the process. You need to get into a routine. Identify u, find your du, find the du inside the integral, and add the missing pieces if you need to. And then you can do your integral. Yes, David?
So why do we find the du if we're just doing the integral of u?
Well, because you can't do the integral of u unless everything else inside of the integral is the du. For example, let's say that I had the integral of 3x cubed times radical x cubed plus 1 dx. Okay? If I were to do that, and I made the u the x cubed plus 1, and the du was 3x squared dx, notice what I would end up happening. I would have the 3x squared dx, and I'd have the radical x cubed plus 1, but since I had a cube originally, I'd have this extra x in there. Okay? So if I did my u substitution, I'd have the integral of x times radical u du. And I can't do that. Alright? I wasn't able to substitute out all the x's. Now there are ways that we can handle it that, like for example this one, there is a way that we could handle it eventually to be able to integrate at this point, but for right now we'd be stuck. Okay, but that's the key. You have to match up everything else inside with your du to substitute out all the x's completely. Okay? Alright? Good.